Now what we're going to do is we're going to talk a little bit about the periodic table, what we can get from there, what we can know about an atom's structure from the information given in the periodic table. We'll talk about a few things like valence electrons, electronegativity, and then ultimately what really matters is how atoms bond. So let's start with carbon. Carbon. We know by looking at this, we've got this 6 above the C. C stands for carbon, and then we've got this 6. That's what's called the atomic number, or the number of protons. So what I'm going to do is I'm going to draw an atom of carbon, and I'm going to put 6p right here for 6 protons. All right, well, now we think to ourselves, how many neutrons are going to be in there? Well, this number right here, this is called the atomic weight, and it's actually an average of all the carbons out there in the world. So you can see most carbons out there in the world have a mass of 12. All right, but there's probably some out there that have a mass of 13 or 14. So if I had a cup of carbon sitting on my desk, almost all of the atoms in that cup would have a mass of 12. But there's a few that would have a mass of 13 or 14, and that throws the average a little bit higher. Well, let's just go with the most common isotope of carbon, and that's carbon-12. Well, we've got a mass of 6 already because protons have a mass of 1. And then we got to ask ourselves, where does the rest of the mass come? Where's the rest of the 6? We need 6 more mass units to fill up carbon-12. So, well, we ask ourselves, okay, is it the electrons or the neutrons? Pause the video, think about it if you need to. Otherwise, I'll tell you right now. It's from neutrons. Neutrons are the ones that have mass. Electrons really don't have mass. So now I've got 6 protons, 6 neutrons for a grand total of 12. Now to add those electrons, what I'm going to do is I'm going to put these rings around here. So electrons are found outside the nucleus, in what we call shells, the electron cloud total. And I'm just going to symbolize electrons with a little dash or a minus sign. This first shell, the one that's closest to the nucleus of the atom, can only hold 2 electrons. It's just that small. The next shell can hold up to 8. Well, we're not going to need 8. We've already got 2. We want this to be a neutral atom. So think to yourself, how many electrons do I want total? We answered that already. It's 6 total. I've already got 2 on there. So I just need 4 more. 1, 2, 3, 4. That's a very simple drawing of carbon. It's neutral and it's the most common isotope. Now, notice this. If we had something called carbon-14, well, then that one has a mass of 14. And think right now, what am I going to change about this to make it still carbon, but have a mass of 14 instead of 12? Oh, all right, pretty easy. It still has to be carbon, so we can't change the number of the number of protons, but we can change the number of neutrons to 8. So that's 14 total. If we were to change the number of electrons, that wouldn't change the mass, that would change the charge. All right, let's go to a different one. Let's go to hydrogen. Hydrogen has a mass of, or has an atomic number of 1, so that's just 1 proton. The most common isotope, and that's the one that I want to draw right now, has a mass of 1. As you can see, there's probably some out there that have a mass of 2, but most have a mass of 1. So wait a minute, how many neutrons am I going to need? The answer, none. No neutrons. Because if I had a neutron, then I'd have a mass of 2. But I wanted the most common isotope of hydrogen. All right, now I want to draw hydrogen, and I want it to be neutral. I don't want it to have a charge. Well, that means right now it's got a positive charge, so go ahead and put 1 electron on there. Now I've got 1 proton, 1 electron. They cancel each other out. This is the most common isotope of hydrogen. Now, a very common ion of hydrogen is what we call H+. Now think to yourself, what are ions? Well, ions are a changed number of electrons. So what am I going to do? Am I going to add an electron or take one away to make it H+? Think about it. A lot of people get screwed up on this if they try to go too fast. What I actually have to do is take this one away. And here's why. Once I take it away, now all I have is one floating proton, just one proton. Well, one proton, that's hydrogen. That's how we define the element. And that proton has a positive charge. There's no negative charge to cancel it out. So we just have one positively charged proton. And that's H+. Let's go to fluorine right here. Fluorine has an atomic number of 9, so we need 9 protons. The most common isotope is not fluorine 18, it's fluorine 19. You see that? If I had a cup of fluorine on my desk, the most common isotope in there would be one that's 19, and then there's probably some fluorine 18s in there too. So we got to ask ourselves, how many neutrons? And it's going to be 10 neutrons to make a grand total of 19. And finally then, let's draw the electrons. Well, let's fill up that first shell. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this is going to be important later, but the outer shell, we fill up the inner one first, then we move to the outer one. The outer shell here is so close to being filled. Now it's just like you when you get just one wrong on a test. You're probably more mad than if you got 5 wrong. Why? Because you're so close. You were so close to being perfect. And that's how this one, we could say that's how this element feels. This atom feels. It's so close. It really, I'm gonna give human qualities to it now. It really wants one more electron really badly. That would fill up the outer shell, or what we call the valence shell, if we had one more electron. All right. Let's now think about, how about helium? Along those notes, let's go to helium. Helium, that 2 says 2 protons. The most common isotope, clearly it's going to have a mass of 4. So easy enough, 2 neutrons. In order to make it neutral, I'm going to give it 2 electrons to balance it out. Now, what's important about helium is that its outermost shell is filled. That is the definition of atomic stability. When atoms have a filled outer shell, they are very stable. When they don't have a filled outer shell, like fluorine, they're quite unstable, and they will react with other elements to fill that shell, or to lose that outer shell entirely. It is the valence electrons that determine how much a chemical is going to react with other chemicals. So, helium is called a noble gas. We say it's inert. It basically just doesn't react with anything. It's just super happy by itself. All right. Finally, I think, why don't we go on and work with, let's go chlorine. Chlorine has 17 protons. Now, you can see that there's probably a good mix of different isotopes out there. So which one? Let's just go with chlorine 35. Well, if we have 17 protons, if I had 17 neutrons, that'd be chlorine 34, so there's actually 18 neutrons. And what do I have to do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not there yet. 11, 12, 13, 14, 15, 16, 17. This outer shell, this second shell as well, and that's as far as we'll go in this course, also holds only 8, holds up to 8. So the valence shell here in this particular isotope of chlorine is, just like fluorine, very close to being filled. So chlorine wants to fill that outer shell quite badly. Not as bad as fluorine, and that just has to do with the fact that these electrons in this shell are further away from the nucleus. They don't feel the nucleus as much, and so it's almost like it doesn't care quite as much as fluorine, but it cares quite a bit. It's so close. It's so close to being full. So it's going to try to gain an electron somehow. All right. So let me just kind of recap something, and maybe I'll do just one more. This outer shell here is called the valence shell, and it really determines the bonding of this element or this atom with another atom. How is it going to bond with something else? Is it going to react with another atom? It's the highest energy. These electrons have the highest energy. They're the furthest from the nucleus. The first shell holds 2, the next shell holds 8, and the next shell also holds 8. All right, let's do lithium. Lithium, atomic number is 3, so 3 protons. Here, 6.9, so I'm going to say the most common isotope is actually lithium-7. So in order to get there, I have to do 4 neutrons. And then if I'm making this lithium neutral, 1, 2, and 3. So here we kind of have the opposite situation. Lithium, you could say it feels like, well, I could gain 7 electrons to fill my outer shell, but wouldn't it be a lot easier just to lose that one? That's how lithium, you could say, feels. It's like, I don't really care. I'm just kind of, honestly, I would rather, and I shouldn't say it doesn't care, I should say it would rather lose 1 than try to somehow gain 7. Now, as we mentioned before, I'm just going to give you a little teaser. Fluorine and chlorine, they were just 1 away from being full. So wouldn't it be nice if lithium could just hand over that electron, and it can. But before I get to that, I wanted to talk about this other thing. I need to talk about this other thing called electronegativity. It's a big word, scary word, but if you're going to write something down about electronegativity, just write, how bad does the atom want electrons? Electronegativity. How bad does the atom want electrons? Well, we've already talked about this just a little bit. So let's think to ourselves. Let's rank a few of these. Let's rank lithium. Let's go with hydrogen. Let's go with chlorine. Let's go with fluorine. But then I think what I want to do is jump to oxygen. 2, 3, 4, 5. I think that's good. Let's rank these elements in order of increasing electronegativity, in order of how badly do they want electrons. Well, let's think about this. We've already covered a couple of these. We remember that fluorine was just 1 away. It just needed 1 more. So it really wants electrons. I'm going to put fluorine way over here. We talked about how lithium had 1 electron in an outer shell that holds 8. So it's way easier for lithium to lose that one. So how badly does it want electrons? Not at all. It doesn't want electrons at all. It wants to get rid of electrons, in fact. So we're going to go with lithium way back here. So high electronegativity, low electronegativity. Really wants electrons, definitely doesn't want electrons. In fact, it wants to lose electrons. All right, let's go with oxygen. I'll draw a picture of oxygen to begin with. Oxygen looks like this. Well, it's got 8 protons, and the most common isotope, oxygen-16, also has 8 neutrons. If it's neutral, 1, 2, 3, 4, 5, 6, 7, 8. So let's see, it's definitely closer to filling this outer shell, the valence shell, than it is to like losing those, because you can think of it, it's at 6 of 8 in that valence shell. So it's far closer to filling it than it is to losing it. Just needs 2 more, or it could lose all 6 of those. So we would say that it definitely wants them more than a lot of other things. So it's over here in this realm. I'm going to put oxygen over here. Let's go back to something like carbon. Well, we drew carbon. If you remember, we had 6 protons, 6 neutrons, filled first shell, and then it was 1, 2, 3, 4 out of 8. That valence shell is about half full. It's about halfway there. So we could say that carbon kind of feels like, well, I could take 4, or I could gain 4, or I could lose 4. I'm kind of indifferent. Kirsten, a student the other day, just mentioned that it's kind of like a senior, 12th grader in school these days. I don't really care. Thought it was a pretty decent analogy. All right, hydrogen. Let's go with hydrogen now, before I put carbon on there. If you remember, carbon was half and half. Hydrogen is going to be 1 proton, no neutrons, 1 electron. But remember, this first shell, its valence shell, only holds 2. So it as well is half full. I could gain 1, I could lose 1, doesn't really matter. So for our purposes, they have pretty much the same electronegativity. They're kind of right here in the middle. C and H. I'll just kind of put them like one on top of the other because they're right in the middle. There are some other ones that are, maybe more this way, like magnesium. You can look that up on the periodic table. It would be more in this realm where it's got 2 valence electrons of 8. So 2 valence electrons of a total of 8. So it could gain 6, or it could lose those 2. So it's kind of in this realm. All right. Technically, these two do have slightly different electronegativities. Carbon's is slightly higher than hydrogen's, but you don't have to understand why, or you don't have to know that. Just know that they're both pretty close together. In fact, that becomes pretty darn important later, especially with these 3 elements. Carbon and hydrogen are pretty much right in the middle. Oxygen is a little bit more on this side because those are very common. Those are like the three most common elements inside you and in living things. And since this is AP biology, that's what we care about. All right, so now finally, because we've got that information, we can start talking about chemical bonds. So in a chemical bond, let's go with something like lithium fluoride. Lithium fluoride. There, knew something didn't look right. Lithium and fluoride. Lithium, I'll just draw that one. So we got 3 protons, we got 4 neutrons, 1, 2, 3. And fluoride, we got 9 protons. Remember, we have, in the most common isotope, we have 10 neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we talked about this one already. Lithium wants to lose this, and over here, fluorine wants to gain an electron. So this is like a match made in heaven. Lithium's like, here, take this electron. Fluorine's like, thank goodness I've now got a filled valence. Lithium is also feeling like it's got a filled valence because, hey, it just lost that outer shell completely, so now it's just got 2 there and over here. Now, if I were to ask what's the problem, you might say, even though this really isn't a problem at all, you might say, well, this one has a charge and this one has a charge. This one lost an electron, this one gained an electron. So first, think about which one's going to be positive, which one's going to be negative. Well, since this one lost a negative charge, we took away a negative charge. That means it's going to be positive, right? It's got 3 protons, but only 2 electrons. 3 minus 2 is 1, a positive 1. Over here, it's got 9 protons, but 10 electrons. 9 minus 10, you could say, is negative 1. So this ion is positive, this one is negative. And if you know, one of the most basic things in chemistry is that opposites attract. We've got a positively charged ion, a negatively charged ion, so what's going to happen is they're going to be attracted to each other. That's what holds them together, is simply like positive and negative. They like each other, so they're always right next to each other. Just like magnets, opposite north and south pole magnets, they're just going to be attracted to each other. So a bond here, it's not a physical structure that holds them together. It's just the attraction between those 2 charges. You might also know, so if you haven't figured it out already, that's called an ionic bond. That's an ionic bond because it makes 2 ions that are attracted by their charges. You might also know of a different bond that we would call a covalent bond. Now when you think, oh, that's nicer, they would share, right? They share electrons. Well, let's look at that in this case. What if these 2 shared? What if they shared these 2 electrons? Well, fluorine over here, be happy. 1, 2, 3, 4, 5, 6, 7, 8. It would feel like it has 8 electrons in its outermost shell, the valence shell. But what about lithium? Lithium wants to either lose this or it would have to gain 7. Well, it has 2. That doesn't do anything for lithium, so this would never, ever happen. They're not going to share electrons. Lithium just says, here, take it. It's yours. All right. So that is something, this is a bond that we would call definitely ionic. All right. There are some others, and I'll leave fluorine up here because I wanted to illustrate a point here, because sometimes you can't, it's not perfectly knowable unless you know certain things. So for example, what if we put hydrogen, 1p? Well, you could say it could lose, and then they would be attracted by this one having a positive charge, this one having a negative charge. So hydrogen would lose and fluorine would gain. Or you could say they could share. And then hydrogen feels like it has 2 in this shell. Remember, this cell only holds 2, so it feels full. And this one also holds 2, or holds 8, but it feels full. 1, 2, 3, 4, 5, 6, 7, 8. Here's the cool thing. In this particular case, it doesn't matter. We don't care. They can bond together. Who cares if it's a covalent bond or an ionic bond? Those electrons, they're not actually, remember, there's no actual physical bond here. Who cares how it's classified? It doesn't matter. Those electrons will be kind of around these 2 atoms, and they're just going to be stuck together. Why are they stuck together? Well, those electrons are moving. Is it because this one has a negative charge, this one has a positive charge, or is it because they're technically sharing those electrons and that holds them together? Who cares? Who cares? Let's go with something else completely. Let's go with oxygen that is found in the atmosphere, what's called O2. All right, so what we've got is 8 protons, 8 neutrons, 1, 2, 3, 4, 5, 6, 7, 8. 8 protons, 8 neutrons, 1, 2, 3, 4, 5, 6, 7, 8. This is also kind of a match made in heaven. I'm going to wind up kind of just doing something funny with my bonds here, but what if they just shared these and then shared these as well? So now this atom over here, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, we've got what's called a double bond. We're sharing two pairs of electrons. And this is a very covalent bond. They're sharing them. One isn't taking them from the other. Why? Well, because one isn't more electronegative than the other. And the lithium and hydrogen that I just explained, I just showed, well, technically, yeah, they're being drawn over there by the, or I meant to say the fluorine and the hydrogen fluoride that I just drew right before this. The fluorine is going to yank them. Why? Because fluorine is way more electronegative than hydrogen. So it pretty much pulls them away. In this case, neither one of these is more electronegative than the other. Neither one has a stronger pull. So those electrons are pretty much shared completely equally between them. Let's try another one. Carbon and hydrogen. So I'll go hydrogen here, 1 proton, 1 electron. That's hydrogen. Remember, it doesn't have a neutron. Its most common isotope doesn't. Carbon, 6 protons, 6 neutrons, 1, 2, 3, 4, 5, 6. All right, in this particular case, what's going to happen? Well, this hydrogen could give its proton or its electron to carbon, and then another one could give, and another one could give, and another one could give. And we could have 4 hydrogens all give up their proton or their electron, and then carbon would have a filled outer shell. Of course, it would have a negative charge of -4, and then I guess all those positive charges would attract to it. Okay, but when we looked at that electronegativity thing, right? Remember, carbon and hydrogen were basically both right in the middle. They're both half full. This one's half full here, half full here. So neither one really has a bigger pull, because technically, if we had 4 hydrogens, carbon could give its hydrogen here, give its hydrogen here, give up all 4 of those electrons. If it gave them up, okay, then it has a filled outermost shell, which would be this shell here. But of course, it would have a positive charge, a 4 plus positive charge. So instead here, since they're both the same in electronegativity, we would say this is a pretty perfect sharing right here. So a carbon-hydrogen bond, they share quite perfectly, because they're both similar in electronegativity. They're both about half full on the outside. So we'd have another one down here, another hydrogen here, another one hydrogen here, another hydrogen here, and we get what's called CH4, or methane. And each of those bonds is very nonpolar. That word nonpolar, what that means is they're not being pulled more one way or the other. This is a very equal sharing. All right. Now let's go with nitrogen and, no, let's not do nitrogen because I don't have that up here. Let's go with oxygen and hydrogen. So if I go with that, let's put oxygen down here. Let's go with 8 protons, 8 neutrons, 1, 2. I'm kind of stagger these out a little differently this time. 3, 4, 5, 6. That's, sorry. 7, 8. There we go. 8 electrons. Now let's bring in a hydrogen. And we'll go with 1 plus here, or 1 proton here, with 1 electron. And you could ask yourself, well, what's going to happen? Well, if I have some sort of bond here, and I have another bond here, could they share? Sure, they could share. could one donate to the other? Well, in this case, the hydrogen would probably donate to the oxygen because the oxygen's almost full, and that would just eliminate the outer shell there. And it wouldn't do that anyway because, then that would just, if oxygen donated, well, then it would still be left with 1, 2, 3, 4 electrons in its outer shell. That doesn't help it any. So, we could donate those, but I'm going to tell you the electronegativity difference between these two isn't really strong enough, right? There's not a big enough difference between this one and this one for oxygen to actually rip those electrons away. So it winds up being a sharing. However, it's not a very equal sharing because, like I said, the electronegativity of oxygen is higher than that of hydrogen. It cares more. It's so close to being filled, whereas hydrogen's like, I'm in between. It doesn't really matter. So sometimes I like to draw their sharing like this. This isn't how it actually is. These electrons are actually floating around, where those electrons are actually pulled more towards the oxygen. Here's how it actually works. Those electrons spend more time around the oxygen than they do around the hydrogen. So they're always in constant motion, they're flying all over the place, but watch my fingers, so they spend more time here, and every once in a while one of them will go out that way and one will go out that way, but it's not spending they're not spending as much time around the hydrogen as they are around the oxygen. Put it like this. When my son's 6 years old, 4 years old, my sons would play together. They shared their Legos. And the thing is, my 6-year-old, he cared a little bit more. My 4-year-old, just kind of playing with Legos. This is fun. Whereas my 6-year-old, no, I want that piece. I want to play with that piece now. So what he did is he would have, if I took a picture of them at any given time, there would be more Legos around my 6-year-old than my 4-year-old. Now, all of them could be shared back and forth. My 4-year-old could touch every Lego. That's fine. But at any given moment, there were going to be a lot more Legos around my 6-year-old than my 4-year-old because he cared more. He wanted them more. They're sharing, but not very equally. So here's what happens. We're going to wind up with those electrons. Yeah, they're shared, but they're going to be more often found over here. Every once in a while, yep, they bop back over there. But this side of the atom, the oxygen side of the atom, right? The oxygen itself is going to have kind of a partial charge to it. Why? Because the electrons have a charge, and those electrons are spending more time over there, and we have 8 protons, but it's feeling like there's even more than that because they're being drawn this way because oxygen wants them more. So think about it. Is it going to have a partial positive charge, or is it going to have a partial negative charge as those electrons are being drawn more this way? Well, if we add electrons, what it's really doing is it's adding a negative charge. So this whole side of the molecule is going to be partially negative. Now I'm not just going to write a negative sign. I'm actually going to write a little symbol. It's called the delta symbol. It means partial. Partially negative. This side is partially negative. And each of these hydrogens are going to be partially positive. So this is called a covalent bond, sure, but it's called a polar covalent bond. And what does that do? Well, it means that this side, the side where the electrons are going to spend more time, is going to be partially negative. The other side is going to be partially positive. All right. So now, using that same concept, stick with that same concept. I'm going to kind of redraw that molecule. You probably recognize that molecule that I was just drawing, though I didn't say it. There were 2 H's and 1 O. So that was water. So I'm going to kind of redraw it just in a simpler fashion. And I'm going to add those little partial charges. And I'm going to add another water molecule. Let's go here, a little bit bigger. Now, what would happen if this molecule over here came close to this one? Well, there's a partial positive there, there's a partial positive there, partial negative there. These are actually going to repel each other a little bit. So this thing would quickly spin around. And as we mentioned before, and as you probably already knew, opposite charges attract. So we're going to put an oxygen here with its hydrogens like that. Partial negative charge, partial positive charge, partial positive charge. There's going to be a weak attraction right here between the oxygen of one water molecule and the hydrogen of another water molecule. Why? Because this oxygen is partially negative, this hydrogen is partially positive. They attract to each other. You've seen this before. You've seen water that is able to, water forms droplets. And you think it's perfectly normal, but a lot of other liquids that don't have this thing going on don't actually form droplets. If you're like me, you've maybe filled up a glass of water and you didn't turn off the faucet right away and it was dripping into it, and you could actually see that there's this dome of water over at the top of the glass, and it's actually bulging over the edge, but water sticks to itself. It sticks to itself. This actually becomes really important in life. This is one of the reasons that water has some very special, this is the reason that water has some very special properties. Water is really hard to boil, as you probably know. Water takes a long time to boil. Why? Well, because it's that energy that goes into boiling water, to turning it from a liquid to the gas, has to go into breaking these hydrogen bonds. We have to give each molecule enough energy that bond between them, that weak bond between them, rips them apart. And I just said what that bond is called. It's called a hydrogen bond. Why is it called the hydrogen bond? Don't worry. I mean, it was because it usually involves hydrogen. Well, they could have called it a lot of other things. They could have called it a partial charge bond. Maybe that would have made more sense. But you know what? They didn't ask me. So they called it a hydrogen bond for other reasons. Who cares? Well, how did that hydrogen bond form? Let's work backwards now. Well, it's there because there's a weak negative charge here and a weak positive charge here. Well, why is that? Well, that was because these two didn't share nicely. The electrons in this molecule are spending more time around the oxygen. They're getting pulled more this way, so it has this partial negative charge. And since they're getting pulled away from the hydrogen, this one it's losing that negative charge, so it becomes partially positive. Same story on this one. So what did we call that again? Oh, that's right. That was called a polar covalent bond. So a polar covalent bond can cause a hydrogen bond to form in a different part between two different molecules. So if there's a polar covalent bond in one part of the molecule, it might mean that it could be that molecule probably is attracted to water, for one thing, because water has polar covalent bonds. Right? So you could have a completely different molecule entirely. Like, for example, let's go with there's a giant molecule, but it ends with N to H. Nitrogen, I'm just going to tell you, is more electronegative than hydrogen. Not as much as this, but it's definitely more. And then this thing could be attached to a huge, big other part of a molecule. This could be a gigantic molecule. It doesn't matter. This part of it right here, this right there is a polar covalent bond because the nitrogen likes those electrons more. It claims them a little bit more often. They spend more time around the nitrogen. So what are we left with? Just like before, a partial positive charge right there. And then from there, we get this hydrogen bond. So this big old molecule, maybe it's a protein, might be hydrogen bonding with water and would probably dissolve very well in water. The same story goes. I'll give you another example, one more example. Of sugar. Sugar, it's too big for me to draw it right now, but it's basically, I'll just kind of draw a very simple sketch of it. C. Let's go with the O right here. There's C over there. There's a bunch of O's and other things coming off of here. Let's go with this one being double bonded to an O. Let's go with O and H, and then this one has an H. So again, I'm not going to draw the whole thing. This pattern kind of repeats. This one might have, that basically has carbons and hydrogens on it. This one, oxygens and hydrogens attached to it. Another one over here maybe has O and H. This one has H here. Remember, carbon and hydrogen share very nicely, but oxygen and carbon and oxygen and hydrogen, they don't share nicely. So what we're going to get, again, is we're going to get partial negative charge here, partial positive charge there, and we're going to get this hydrogen bond thing occurring if we drop sugar into water. And this is why, if you put a bunch of sugar into water, have you ever seen how much sugar can dissolve in water? It's crazy, because all these little water molecules are attracted to all these little areas where electrons aren't being shared equally, and the negative end is going to be attracted to any partial positive charge, and the partial positive charges are going to be attracted to over here where we've got some partial negative charges. Finally, I guess that really, for our purposes, demonstrates those three types of bonds. Let's review them. Ionic. One atom actually donates some electrons to another. So then one becomes positive, the other becomes negative, and they're just attracted to each other because of that. In a covalent bond, electrons are shared, like in this bond. In a nonpolar one, in a nonpolar covalent bond, then what happens is those electrons are shared really equally, like between two hydrogen atoms or two oxygen atoms, right? Because neither one is pulling them closer. Between a carbon and a hydrogen, because they both care about the same. In a polar covalent bond like this one, the oxygen, yeah, they're sharing, but the oxygen likes those electrons a little bit more. So it pulls them a little bit closer. In our next unit, we'll learn about things called functional groups, and those are just basically, like I said, this is just preview. This is just a little teaser for you. Those are groups of atoms that typically have similar properties to. They bestow similar properties upon the bigger molecules that they're a part of. So this right here is one of those functional groups. In fact, I'll just do this. COOH. And what happens here is these oxygens really are pulling electrons towards them. They're pulling them from the carbon. They're pulling them away from the hydrogen. They are this whole area right here becomes very negative. Right? This becomes very negative. The whole area. Of course, this guy becomes very positive. Very partially positive. And what can actually happen is if a water molecule comes along, remember there's a partial positive charge here. Whoops, I drew that one backwards, didn't I? I did it the last time too. Flip it around here. The partial negative charge here is attracted to that partial positive charge. And because those electrons are being pulled so close to these oxygens, are being pulled away, this water molecule can actually strip that thing right off of it. It could actually pull it away. And that would give this whole molecule a full negative charge because that proton got pulled away, but its electron stayed over here. That's just a little preview, so if you don't get that yet, it's very common. It's okay. But this is a very common thing to happen if this particular thing is attached to a bigger molecule. All right. I think that's it for atomic structure, valence electrons, electronegativity, and bonding.